S not equal to the empty set out of S squared. All right. I promised myself I wouldn't spend too much time on this because I actually want to get to the interesting things. And so I'm going to move right along and now just give you a higher level overview of the proof. And then go from there. So this is the goal. All right, so let me remind you what we're trying to do. We're trying to show that the characteristic function of our random variable is not so different from the normal characteristic function. It's small. And so this is kind of the small for t small. And so the basic way that this is done is there's two cases. And saying there's two cases is a lie, and I'll tell you why it's a lie, but it's okay. So one is you're going to have t is large. And then in this case, it's you show this is true by referring to Justin and Swasti. They have a very nice trick for this case. And they just do it, and I'm not going to show it, but it's not what I did, but you should look at their paper because it's very nice. And then you have t less than root n, and so here you do something else entirely. You take a look at your random variable, and what you're going to show is that when you're in this regime, you can say something like the following. T, the number of triangles, is determined almost entirely by the number of edges in the graph. Right. And so this is the somewhat surprising conclusion that you can get to by going through this Fourier basis in the following sense. That more explicitly, if you ask me, you come up to me and you say, how many triangles are in ask me this. Are in a graph G. So then I'm going to come back and I'm going to respond by asking, how many edges are there? And you'll tell me. So you'll give me some number, and I don't know what it is. You'll answer E. And then I'm going to make the following crude guess. I'm going to say, okay, if there's E edges, each edge E should be on how many triangles? Well, so you fix your edge. And ask me how many triangles is it on? Well, there's n minus 2 other vertices that you could try and make a triangle out of it with. And each one of these makes a triangle with probability a quarter. Right, because each edge is there with probability a half, so each triangle is there with probability a quarter.
The t is not away from the mean. It's not t minus mu.
Oh, so sorry. So this is.
Oh, t is already adjusted.
This is the. So this is. So I've swept something under the rug, and then I've confused things with having little t and big t.
Yeah. So you said.
So I apologize for the confusion.
Deviation for the mean.
Right. So little t here is the input to the characteristic function.
Okay.
Yeah. And phi, you're absolutely right. You said he had to normalize somewhere, and I did. I didn't write down what this was the characteristic function of. It's of the centralized, normalized version of the random variable. I just didn't want to say it. But it's true, you caught me in a lie.
Yeah,
that's right. All right. So you ask me how many triangles in the random graph. You tell me how many edges there are. And I'll say, well, each edge is probably on about n minus 2 over 4 triangles. Right? So all I do is I say, okay, So therefore, the number of triangles is roughly the following. It should be the number of edges times each one of them being on n minus 2 over 4, and I guess I should divide by 3, right? Because I counted each edge, each triangle 3 times in this manner. And so the somewhat surprising answer is that this estimate is very good, right? And so how good? This estimate has error about n to the 1.5, which is very good because there's about n cubed triangles. So our error is very small. And the standard deviation is n squared. That n to the 1.5 versus n squared is probably related to the square root error that I get at the end. I say probably because I can't actually, this is a heuristic, the proof doesn't look like this question, but this explains kind of the idea that's going on there. All right, and so this is going to let you get a bound on your characteristic function, and why is that? So, let me set this up. So let's say I want to compute the expectation, and so now I am going to have to do the normalization to show you. I want to compute the expectation of my normalized random variable. And so the goal of the game will be to look at the characteristic function of this random variable. Sorry, is this hard to see? I can see that people are... Is the chalk not clear enough, or is it just not bright?
It's invisible chalk.
Is the orange chalk going to ruin the board?
Yeah, don't worry about that.
Okay, thank you. All right, and so the point is that what we're going to do is we're going to say that this is going to be... Is that worse or better?
Worse. Worse.
Pink. Yeah? Okay. All right, so we're just going to stop here. And so what we're going to note is we're going to say, what we're going to do is we're going to put, what you end up with here is roughly the edge count. The normalizing won't matter here. And so you'll have the number of edges. So this is a heuristic, but it's the right one, and it follows the proof almost exactly. And then you're going to have some, whatever your error term is here, which I'm going to call y. And so the trick is that you say, okay, well, we said that the error term was about y over sigma. We said that the error term was about n to the 1.5, so I'm going to hold myself to that claim, right? And so what we get here is that this is roughly e to the it number of edges divided by sigma, and then plus n to the 1.5 over sigma. And sigma is about n squared, so this is about 1 over root n. Yeah. So you'll just take my word for it. So you get something like this. And so now 1 over root n is small, and so all I do is I take something very blunt. I'm just going to take the mean value theorem and pull this out. The derivative of this complex exponential is always at most 1, because it's, yeah. Right. So it's just, and so what you get is that this is, I'm going to keep drawing squiggles, so you can't, even if I'm wrong, you can't say I'm wrong, because the squiggles could mean whatever I want. And so what we'll have here is about this, the characteristic function of the number of edges plus some noise, which has size about 1 over root n, or t over root n. I'm not going to hide that one from you. All right. And so now, here is our sort of 1 over root n error term. And now this is the number of edges. But the characteristic function of the number of edges, so the number of edges in a random graph is a binomial distribution, which is incredibly well studied. And so you go into your favorite book, I went into Petrov's in Sums of Independent Random Variables, and you look up whatever Berkowitz bound he says was best back in the 70s, and you use it. And so you get that this is roughly the normal distribution, the characteristic function of the normal from this guy. and then plus your error term. The error term you get out of the Berkowitz bound here is much better than the error term I get out of this, so I'm just excluding it. And then that's how you would show that the characteristic function is almost exactly the characteristic function of the normal, plus some error here. All right. So that's still 7 minutes, so I'm not going to give you any more details than that, but that's the high-level view of the proof. And the ingredient that you go through it is by, which I don't think I'll have time to do, sadly, so I set up the Fourier basis, and I won't really show you where it comes in, but you use it to get this estimate. And so there's a couple things that you might notice. That one is that this breaks down very badly when t is about size root n. And so you work through that, and if you do a little bit of more estimating, then you can get a slightly better bound. So you wind up with something that actually ends up, I think if you work a little harder, you get something that looks like the following. You get e to the negative t squared over 2, and then the error term that you get over here is it's not going to be actually worth my time to find, is it? And this will, you can then optimize, and so this will work out a little better, and you end up getting the result that you want. All right. And so there's some important things to note here, which is that this breaks down badly when t is about n. And this, I claim, is for good reasons. This is not because I was lazy. This is because my approach can't handle that. And I'll mention why, sort of in the conclusion here, which is part of the remaining questions. All right. So I'm going to move on now. So, so that was the proof. That was the result. And so now I want to move on to sort of questions. And so for this one, we ask, so take an arbitrary graph H. And then you can ask the following question. You can make the subgraph counting random variable and ask, how does the random variable, given by the number of copies of H in your random graph, behave as n goes to infinity? So central limit theorems are really well understood. These were talked about in the 80s, and Ruchinsky basically gave an answer that covers any P, any graph you want to look at. He sort of told.
And the same technique as triangles is not much harder?
So the technique for triangles was done in 83, I think also by Ruchinsky, but I can't remember if it was actually him. And it was an easier technique, and then he did something a little more a couple years later to get everything. So triangles were actually known first. Anyway, so this is well known, but then local limit theorems are totally open. The only ones that are known are edges and triangles and V's. So edges is just a binomial, so it's just trivial, but I thought I'd mention it. Triangles, this was done by Swastik and Justin, and then the next one is the number of graphs that look like this induced. So saying it's a triangle, but one of the edges is not allowed to be there. And so this, that was, I guess you just write B, that was me. And everything else, it's unknown. And so this is interesting both because we suspect that most graphs, like complete graph cycles, these things probably have local limit theorems. And you might be tempted to say, well, we can almost always get a local limit theorem, but I want to give one cautionary tale which surprised me. And so I want to make sure that I share it with you, which is that if you look at central limit theorems, in the world of central limit theorems, not all graphs have a CLT for subgraph counts.
Even constant graphs.
Constant size graphs, exactly. Yeah, so they do if you're counting homomorphic copies. But if you're counting induced copies, there's a counterexample found by Janssen and Nowicki. So let me, all right, Janssen and Nowicki found the following graph for induced subgraph counts, which they said did not obey, at least for certain regimes, does not obey it. And I have a picture of it here, so let me, it's a wheel. Wheel with 7 spokes. And so this graph, for whatever reason, for induced subgraphs, I think has a different limiting distribution than the normal. So if you count homomorphic subgraphs, it is normal. There's nothing that could stand in your way. But induced copies...
so that's different than this. This is actual exact copy.
So this one is just, this one would consider if you found a K8 would be said to be containing a bunch of these, whereas an induced subgraphs, a K8 would have none of these, yeah. So induced subgraphs is a harder question just because you're asking for a little more detail.
So you converge all the limiting distribution?
What?
It converges, but it doesn't converge to the normal?
Right, I think they do say, they say something
about...
about...
What it does?
What?
Do you know what is distribution, the limiting distribution?
I think they just say to a non-trivial. I don't. They probably say I don't remember.
Yeah.
Well, it's probably skewed, they say.
Yeah.
No, maybe they don't know the distribution.
Or I suppose
no more.
I should humbly admit that this was me reading the paper. It's very possible the paper of Janssen and Nowicki. These were very smart guys, and I'm just me. And so it's very possible that I misread them. So if you go and check it and it's false, just blame me. It's not their fault. But so I certainly don't remember the... I can tell you that I was curious because for this graph, I could prove central limit theorems for most other graphs using my technique. But this graph I couldn't get a central limit theorem for. So the fact that they said it didn't have one made me feel better, and so maybe I was just very willing to believe it. And so I have 10 seconds left. But so then allow me to just not write it down, but to repeat, I am interested in knowing knowing when are there local limit theorems, and in particular, if you could give me a good way to even just estimate, trying to sample these things randomly, the error that you get is so much larger than the actual output values. And so this is where I would have pulled this thing down again, but just trust me that the histogram, if you sample it just naively, varies somewhat wildly for local limit theorems. For central limit theorems, it buckets out nicely, but local limit theorems, it's just sort of very hard to sample these and see the truth. And so if anybody could think of a good way to get around having to compute everything and 2 to the n choose 2 time, I would be very thankful. So maybe I'll stop there.
Well, isn't it that you're trying to estimate the density function as opposed to the distribution function? So in other words, you're trying to estimate the derivative. And
Yes,
so naturally,
yes.
it's harder to get the derivative than
Yes.
to get the original function. And
Yeah,
so
yeah.
naturally, it's going to be more difficult.
Yes.
So the same technique did not work for the next difficult graph? Like a
yeah, so...
cycle of Lex form?
Right, yeah, so I really wanted it to. So the next one that I tried was a K4. And so this one I sampled on my computer and I couldn't tell if it was true. And so the problem is that you notice that, so my technique broke down somewhere around, so my technique for estimating the characteristic function, it sort of fails when you have t, the input to the characteristic function, about n. And this is true regardless of the graph you input. Which is nice because it means that you could use this to get central limit theorems for almost any graph, and in fact, you get the following thing as centrally limit distribution. Take the number of copies of pairs of edges. You can show that the characteristic function of this is small up until about Tn. And so you get a central limit theorem for pairs of edges. Of course, you can't hope to get a local limit theorem for pairs of edges because it should always be roughly a square. It won't work. And so, sorry, you'll have to forgive me, I'm tired. What was the original question? I know this was part of answering it. It was, oh, can I get K4s? Right.
Yeah.
And so my method breaks down because it covers this. So it can't go the whole distance. It goes up to about t is about n. And so Swastik and Justin, they were able to cover for t greater than, And I think it's something like this, m to the k. So I think, is that right? Where k is the number of vertices in your graph. Maybe. Is that right? So then when it was 4, they were able to cover up to 2, yeah, they were able to cover up for t bigger than n when k is 4. So then our methods both break down at the same point and nobody can cover this intervening range. So this is currently, I can handle any graph smaller than size 3 and no graph bigger than size 3.
And you believe that there is a local limit?
For some of them, not for, I have no idea what to expect. I assume most things look normal, so I expect local limit theorems, but I was wrong when I guessed that it would be true for all subgraphs, so I'll hold my tongue on making any guesses. Yeah.
Okay, no. Next week's speaker is our own.
This week's speaker was someone else.
Yeah. So.